Voy a aprovechar estos primeros momentos para explicar un poco la dinámica que vamos a seguir. Antes de nada, bienvenidos a esta sesión de Física Solar de la reunión virtual de la SEA, que está organizada por Consuelo Cid, Sara Esteban y yo mismo. Tenemos 15 contribuciones y 40 minutos. Entonces, hemos pensado que la mejor forma de dar la oportunidad a todo el mundo de presentar su trabajo es mediante una pequeña presentación de una o dos transparencias. Somos 15, debe haber un pequeño tiempo para las preguntas que puedan surgir. Por tanto, hemos asignado 2 minutos a cada uno de los participantes. Con esto llenaremos 30 minutos y nos quedarán 10 minutos para preguntas y comentarios. Daros cuenta de una cosa, si tardamos 2 minutos y medio cada uno, nos vamos a 37 minutos, 38 minutos y ya no hay tiempo para preguntas. Con lo cual vamos a ser muy estrictos con los autores. Voy a avisar del tiempo que queda, digamos, cuando queden 15 segundos, para terminar, voy a avisar al autor y, por favor, hay que terminar casi inmediatamente porque si no, el resto de los autores no pueden presentar su trabajo. Aquí arriba en la pantalla veréis un reloj. Cuando empecemos la sesión, pues se pondrá 0. Podéis mirar cuándo empezáis y sumarle 2 minutos, de manera que tenéis una idea más o menos exacta del tiempo disponible. Yo creo que esto es todo. I would like to ask whether we can make the presentations in Spanish or if you prefer us to speak English. I don't know if we all speak Spanish.
No, sorry, I will give the 2 minutes talk in English if it's possible.
Okay, no problem at all. I mean, perhaps in that case, we should all speak English. So, yeah, I think it's time to start. Let me restart the clock. And just a second. And Carlos, you are the first
yes.
presenter.
Yeah. Okay, so as I have to go very fast, I would like to give you a summary of the main things and main new developments that we have done for the European Solar Telescope. We are doing several things at the same time right now with the target of making ESC as a reality. We are undergoing several calls for tenders. These are for the main elements like the primary mirror, secondary mirror, telescope pier. We created a board of directors that we think that they will help us increasing the interaction between the EST project office and the different governments from the different countries that participate in the mission. We are hiring several people, so our team is getting bigger and bigger. We are now 26 staff. We are creating also specific groups to revise the science requirements and also to define the instrument specifications. And the main goal is to have everything ready, the full construction proposal by the end of 2022. So then we can start the construction in 2023. And we hope that we will see first light by 2028. And it means that we are very excited because we are in a critical time where we are defining the future of the infrastructure. And we think that we will fulfill the dream of having a European solar telescope that will be built by multiple institutions from multiple countries in Europe, working together to have one main telescope. That's all. Thank you.
No, the previous one is mine.
Manuel.
Sí. Anterior. Esa. Vale, pues what I am going to do is to introduce you a bit the work that we have done to validate the SMOS mission as a tool for space weather. SMOS was never designed for solar observations, but it is affected by a contamination of solar origin at 1.4 gigahertz that can then be used to extract the solar radio burst, and with them we can monitor, previous slide, the problems, for example, for the GPS, Galileo, or navigation radar. What you can see in the two images below, one is a problem of false echoes in night traffic control radar, and on the red corner is pretty much the total loss of log of the GPS satellites. So in the next slide, what we can see is just a mix of, let's see what SMOS can see. The two first images are just a test to prove the sensitivity of the instrument to weak signals. One is the solar activity cycle, the other is the solar rotation. SMOS was able to detect both without a problem. On the upper right corner, you can see the polarization of a radio burst. It detects both circular polarization and linear polarization, what is very, very new detection. And the images from below are basically about the connection that exists between the radio emission at 1.4 gigahertz and the CMEs. In fact, it has been possible to detect originally missed CMEs in the images thanks to the radio emission. And that's all from my side.
Luis, no se te oye.
You are muted, Luis. You are muted.
Sorry. I cannot control simultaneously the Zoom teleconference and the keynote presentation. So this is why I couldn't unmute myself. One very quick reminder, I forgot to mention that if you have questions or comments, please write them in the participant chat so that we can have them together for the last part of the session. Okay, and I'm going to restart the keynote presentation now with a clock. Yeah, exactly. So the next presenter is Carlos Larrodera.
Yes, hello. Okay, I am here to present our work that is called Bimodal Distribution of the Solar Wind at 1EU. And we have used data from the ACE spacecraft during the time range between 1998 and 2017. And we have information about the solar wind, about the speed, the proton density, the proton temperature, the proton speed also, and the magnetic field. And we apply a Gaussian probability distribution function to this data in two different datasets, the whole dataset and a yearly dataset. And in the next slide, please, we can see in the right figure, we can see our result where the gray area, it's the data, and the blue and green fits, it's the individual Gaussian, and the red one, it's the big Gaussian. And we can see that the fitting, it's the big Gaussian fitting, it's appropriate not only for the solar wind speed, but also for the density, the temperature, and the magnetic field. On the left side, we can see our result where we can separate the solar speed, the solar wind, sorry, into the slow wind and the fast wind. And here is our results. And we are able to see that there is some correlation between the parameters that we obtain from the fitting, especially for the magnetic field and the proton density. In the proton density, the correlation is around 0.6, and in the magnetic field, it's around 0.7. And that's all. Thank you.
Thank you very much. I think the next speaker is Consuelo.
Yes, hello. This is just to talk about the Tenerife blackout that happened last September 29. When we were just watching the news on TV, we were aware about this blackout, and then we start searching what happened at the geospace environment. Well, we discovered that the indices, the magnetic indices for many places, but also calculated from Weimar Observatory at Canary Island, were disturbed. Not too much, but were disturbed. On the first plot, you can see the disturbance. It is moderate, but there is some disturbance. The red plot, the second one, has a local current index for geomagnetically current induced. And well, it is not getting so large values, but it is continuously fluctuating. Since what is called the storm sudden commencement, that is with the vertical green line, and the blackout was exactly at the time where you have the red line. Well, why this happened? Of course, you have more information here, but please go to the long presentation. Well, what we can find on the solar wind is that a fast stream is just coming after a slow wind. So that is the first thing that we can see. Can you please go to next slide? Yes. Well, that fast stream is coming from the central coronal hole that you can see here on the solar image. But all this coronal hole is, let's say, not enough to make a so large danger as it probably made. What we also discovered, not only in solar wind, but also in the sun, that there was a CME. That CME can be seen, well, I will tell you that the CME was probably coming from the place where the arrow is pointing on the solar feature, on the solar image, but you can see here two coronagraphs. One of them, the one on the middle of the slide, is from stereo. Stereo A, you have the image on the top corner. Stereo A was...
Well, we have to finish.
Yeah, sorry. Well, stereo A and B has seen the same CME, and then you can see also a filament. So we have everything to get that solar wind. So that's all from my side.
Thank you, Consuelo. So let's move on to the next presentation by Marta.
Hello. So start?
Yes.
Okay, good. So hello. Well, I'm presenting this work that studies the evolution of magnetic properties on solar pores. And the motivation is to compare the behavior of umbra in sunspots and in pores. So based on ground-based and space-based analysis, it was formulated the Urcha criterion. Because in a statistical study it was found that the umbra-penumbra boundaries are characterized by a constant vertical magnetic field. However, during the formation and decay phases of the sunspot, it's not the case. The vertical magnetic field is weaker. Next slide, please. So we analyze, we are doing a statistical research, but this is a special case because in this pore we can see two different formation periods. In the first formation period, the vertical magnetic field is weak, but it gets stronger and it reaches what we call the stable phase. And we state that this value of the vertical magnetic field is the critical value for the pore. And the area is stable, and the critical value is the red contour. So there is a big increase of flux. The pore grows a lot, but the vertical magnetic field doesn't increase as much as before. So quickly the decay begins. And it's interesting because only in areas with a weaker vertical magnetic field than the critical value, we see that a light bridge divides the pore. And actually in the last map, you can see that the upper region with a weak vertical magnetic field, weaker than the critical value, it decays much faster. So we are studying if this is the case for more cases, more pores, and how we can extrapolate this in a more general way. So thank you.
Thank you very much for being on time, Marta. And the next speaker is Jaume.
Yes. Sorry, I prepared the talk in Spanish and I'm not be able to be in time if I talk in English. Sorry about that. So sorry. Bueno, aquí vemos unas observaciones espectropolarimétricas de la línea subordinada de H-alfa del hidrógeno en el limbo solar. Estos datos fueron tomados el año pasado con el espectropolarímetro SIMPL en Locarno. Podemos ver una variación espacial a lo largo de la rendija en la polarización lineal. Thank you. Si nos fijamos en el parámetro de Stokes Q, la forma del perfil es similar al observado por Gandorfer et al. En el año 2000. Estas variaciones espaciales pueden ser debidas a variaciones espaciales del campo magnético que a través del efecto Handle modifican la polarización lineal. Por otro lado, también pueden deberse a la dinámica del plasma. Next slide, please. Para investigar más estas variaciones espaciales, hemos resuelto el problema del transporte de radiación polarizada fuera del equilibrio en un modelo 3D de la atmósfera solar utilizando el código Porta. A partir de estos cálculos teóricos, hemos simulado observaciones con el instrumento SIMPL y vemos que aparecen variaciones espaciales similares a las observadas en la polarización lineal. El próximo paso es investigar el origen de estas variaciones espaciales en los cálculos teóricos y caracterizar cómo se deforma el perfil de Q y U usando técnicas de Machine Learning. Thank you.
Muchas gracias, Jaume. Sorry. The next speaker is Tobias Felipe.
Hi. In this work, we study wave propagation in solar active regions. More specifically, we analyze two models proposed for understanding these oscillations. On the one hand, the chromospheric resonant cavity, and on the other hand, waves that can freely propagate. This work is directly related to the recent paper by David Jess and collaborators. They claim the detections of evidence supporting the chromospheric cavity. Basically, they took observations in helium-10-830, what I show here in the bottom panel, and in the power spectrum, they found this power peak at high frequency, indicated by an arrow. Then they developed two numerical simulations, one of them with a resonant cavity, the other without the resonant cavity, and only the first case that I show here in panel A shows this power peak. So they conclude that this power peak is an evidence of a resonant cavity. In this work, we do a similar analysis. We perform numerical simulations and we compare them with observations. Next slide, please. The first conclusion that we get is that this power peak is not an evidence of a resonant cavity. Why? Because simulations without a resonant cavity can also produce a similar power peak as a result of non-linear effects. However, we found unequivocal evidence, proof of this resonance above South Ambra. Comparing these observations, we have found that the best observable to distinguish between both models is the phase difference between velocity and temperature. In the case of a resonant cavity, we expect a phase difference of half V, and this is what we measure in the high chromosphere, in the helium-10-830, at the bottom left panel here, and also at the low chromosphere, at the sodium D2 line. In this work, we also propose a new seismic analysis to prove Ambra chromosphere, and that's all.
Thank you, Tobias. It was exactly 2 minutes. So our next speaker is Asaimi. It's your turn, Asaimi.
Yeah, hello everyone. Well, in this work, we studied the magnetic properties of penumbral microjets. We focus in those with short durations and use observations from CRIS in calcium 8542. So we analyzed 36 microjets characterized by emissions in the wings, particularly in the blue wing, and frequently also in the line core. Interesting findings were that the line core intensity normally remained slightly enhanced during longer periods than in the blue wing. The brightness regions are radially shifted when observed in the core or in the wing, which can be explained as a projection effect due to the expansion of the magnetic field with height. The microjets have enhanced polarization signatures that stand out both temporally and spatially. And in order to retrieve information of the magnetic field in the upper photosphere and low chromosphere, we apply the weak field approximation in the wings and in the line core. The microjets show transient perturbations in the photospheric field, which were classified in 3 different types according to the changes in the inclination and field strength. And such changes were generally much smaller in the chromosphere, but of up to 100 Gauss in a few cases. Our results are interpreted as upwardly propagating perturbations of compressive nature that likely originate in the photosphere due to magnetic reconnection. And the enhanced line cores suggest that the temperature increases in the chromosphere, but inversions are necessary to quantify this and to understand why such heating seems to last for longer periods than in the photosphere. That's all.
Thank you, Asaimi. Our next speaker is Sergio. Are you there, Sergio?
Yeah, I'm here. Do you hear me?
Yes.
Okay, so yeah, I'm going to present a paper that we published at the beginning of the year about our filament system. Could you please go to the next slide? The filament systems are cool loops seen in the chromosphere. You have here in the left a little bit of a scheme of that. These loops are connecting two different polarities. Normally the plasma is going up in the center where you see these blue lines up, and then the plasma is going down along the loops to the food point. Yes, exactly. So we are interested how this plasma it is going up, but more importantly, how it is coming back to the lower layers of the solar atmosphere. For that, we observe a small emerging flash region you see here in the right with two pores. These two pores have two different polarities, and we observe with two different telescopes, with Gregor and SST. To try to follow this dynamics, we need to observe different layers of the solar atmosphere, and for that we need several lines to be observed at the same time to observe in different layers. You can see them, we observe with Gris in Gregor, with the helium 1030, silicon and calcium, so it's the infrared, and with Gris in the SST with the calcium and 2, the infrared, and the iron line. The loops, can you come back? The loops that you can observe in the chromosphere are this in the helium and in the calcium, that they are in the middle. And if you go into the next, yes. So you can see here in this with these arrows that with the helium we are observing the upper chromosphere, then the lower chromosphere in the calcium, and then the other three lines in different parts of the photosphere. So we are interested in to calculate the velocity in one of these food points that I showed you before, and I calculate this mean velocity inside of this food point, and we saw some similar behavior in three different lines in the helium, calcium, and silicon. 2 chromosphere and 1 silicon. You see here in the food point 1, in blue, the helium behavior.
Your time is almost up. Hurry up.
Okay. So basically here we see that we could follow the plasma in the food point through 3 different layers of the atmosphere. So, and that's it.
Thank you very much. So we move on to the next presenter, Christoph Kukan.
Hello, everybody. Good afternoon. I'm going to shortly report on our latest work that we have published a few weeks ago. It's about a solar filament eruption, which was observed with the Gregor telescope in 2016. Filament eruptions in general are very difficult to observe because they are unpredictable, and with ground-based telescopes you need to be in the right moment to really catch them. So this was a quite lucky observations that we had back in 2016. In the middle you can see an HMI magnetogram. Overplotted you see the in red the filament, and then you can see the two lines, yellow and orange, which are the slits, in this case, from the slit spectrograph GRIS. So we observed 3 maps in total, small maps in the helium 10830 spectral range. On the right side, we see some examples in intensity of the spectral range. As you can see, they are quite different in shape. So what we first did to analyze these profiles was to classify them with a machine learning algorithm called k-means. After that, we obtained 30 groups of different types of spectra, and that we inverted with the Hazel inversion code. So in the next slide, I'm just going to show you 2 of the results of the maps, the physical maps that we got. On the left side, you can see the line of sight velocities, where you can see in the lower part that we found Doppler shifts into the blue of up to 73 kilometers per second in the chromosphere. And on the right side, I'm going to show you the azimuth of the magnetic field. And as you can see, it is interestingly that the field lines in the erupted filament part, which is in the middle, has rather smooth field lines, not really mixed or twisted ones. So yeah, I invite you to have a look to the paper and to the longer presentation. I'm open to any question. Thanks.
Thank you, Christoph. So we now move on to the next contribution by Mateusz Kryginski.
Hello, can you hear me?
Hi, yes.
Okay, I'm here to give a short summary of the work I wanted to present. And as the title suggests, this work is focused at the attempt to infer magnetic information about off-limb spicules and also coronal rain blobs. For this purpose, we make use of several spectral polarimetric observations of the calcium-2 8542 line taken with the CRISP instrument at the SST, which contain both spicules near active regions or in quiet sun areas. We use the weak field approximation to infer the line of sight component of the magnetic field through a Bayesian inference scheme. Next slide. We applied our method of inference to spicules without any spatial or temporal averaging, while for the coronal rain blobs, we needed spatial averaging. Here you have 2 examples of the type of results that we got for spicules on the 2 histograms on the left. Independently of their location, spicules show magnetic fields of the order of hundreds of Gauss. The difference we have seen between quiet sun or active region spicules is that the inclination with respect to the observer for active region spicules is very fixed, yielding line of sight components of mainly 1 sign, depending on the dataset. This inclination is not fixed for quiet sun spicules, and so both signs are inferred. Coronal rain results were less numerous, as you can see on the right, but we have also found magnetic fields of the order of hundreds of Gauss at low coronal heights. And that's basically it. Thank you.
Thank you very much. And the next contribution is by Sergio Díaz Suárez.
Hola, well, I am going to do my talk in Spanish. Sorry for the English speakers. Bueno, soy Sergio Díaz y voy a explicar brevemente la contribución que he hecho junto con Roberto. Ante la primera evidencia de ondas torsionales de Alfvén en la corona, hemos querido modelar este fenómeno teóricamente. Para ello hemos usado un modelo sencillo de bucle coronal con una capa de transición inhomogénea una capa de transición homogénea radialmente entre la región externa y el interior del tubo, ambos homogéneos. Este tubo está introducido, como veis en la diapositiva, dentro de un campo magnético uniforme y recto que apunta en la dirección Z. Y básicamente, sí, eso. Sí, y bueno, los planos básicamente, los planos superior e inferior, ¿vale? Lo que van a representar son las condiciones de la fotosfera, a las que se le imponen condiciones de atadura. Entonces, a este tubo lo que hacemos es introducir una perturbación torsional en la componente de la velocidad y dejamos evolucionarlo en el tiempo, durante el cual las ecuaciones de la magnetohidrodinámica en 3D son resueltas con el código Pluto y usando malla adaptativa. Así como podéis ver en la otra diapositiva, os muestro 6 paneles en los que se ha hecho para una configuración particular. En los 3 primeros paneles de arriba lo que os muestro es una sección transversal del tubo para 3 tiempos de simulación distintos. Inicialmente, para la densidad en concreto. Inicialmente lo que se observa es que no se ve ninguna perturbación, ya que las ondas de las VEN son son básicamente incompresibles, por lo tanto no sufren. Sin embargo, hacia el final de la simulación, básicamente ya debido a la inestabilidad Kelvin-Helmholtz se sufren las perturbaciones consecuentes, y es básicamente porque las ondas sufren efectos no lineales. En los 3 paneles de abajo lo que muestro es los mismos cortes del plano y los mismos tiempos de simulación, pero para distintos tiempos, para la componente azimutal de la velocidad. En ella lo que se observa es una alternancia de valores positivos y negativos de la velocidad, y es básicamente el fenómeno de phase missing, que es el responsable de los flujos de cizalla que al final provocan la inestabilidad Kelvin-Helmholtz. Y el objetivo con todo ello es ver el papel que juegan las ondas de Alfvén torsionales en la dinámica de bucles coronales. Y con ello termino. Muchas gracias.
Muchas gracias, Sergio. So we continue, and our next speaker is Valeria Liak.
Hello, everyone. I present our work of large amplitude oscillations in flux-rope solar prominences that based on 2.5D numerical simulations using mantra code. We formed our flux rope from the initial shear arcade using different initial shear angles, and after flux rope formation we loaded prominence mass in the region of the dipped magnetic field. After some relaxation we perturbed prominence in horizontal and in vertical direction that you can see in the central figure. Then we analyzed these motions in the position of the center of mass of different magnetic field lines. The results in different models you can see in the right figure. There you can see red diamond is the longitudinal period of the longitudinal oscillations. This period decreases with height and shows good agreement with the pendulum model. That means that the main restoring force for this type of oscillations is gravity projected along the magnetic field. The period of vertical oscillations remains constant with height, suggesting a global normal mode. The periods of different types of oscillations show only weak dependence on this parameter of the structure as shear angle or density contrast. Next slide, please. In order to study mechanism of the external Laws triggering, we placed our perturbation out of the flux rope, and here you can see the results. Perturbation reached the flux rope and displaced it, and the prominence together with the flux rope. In the center figure, in these panels, you can see that external perturbation can trigger both types of oscillations, longitudinal and transverse vertical. Vertical period remains constant with height. You can see this in the right panel. And in the left panel, you can see longitudinal period that decreases with height. The properties of these oscillations are a mixture of those excited by the purely horizontal and vertical driving. In general, in our study, we investigated properties of the different types of oscillations in different prominence models, and also we showed possible scenario of the external triggering of large amplitude oscillations. All the figures and complete study can be found in our paper. Thank you for attention.
Thank you very much. And then we have our next contribution by David Martinez Gomez.
Hello, everyone. In this presentation, I'm going to comment some results about our study of the Birman mattering mechanism in partially ionized plasmas. This mechanism is an non-ideal effect that allows for the creation of a magnetic field from a spatial variation of the density and pressure of electrons. And this effect can be very important in the study of the origin of the magnetic field in many astrophysical scenarios. But most of the research about this mechanism has been done using single fluid models. In this work, we have followed a different approach, and instead we use a two-fluid model that has been implemented in the numerical code mantra. So we have performed two D simulations of the Kelvin-Helmholtz instability in partially ionized plasmas, and we have studied the effect of the charge-neutral collisions on these battery mechanisms. So the plot on the left shows the evolution of the density during the development of the plasma, of the instability, sorry. And the right plot shows the evolution of the magnetic field. The dotted lines correspond to simulations where there is no coupling between the two fluids, and the solid lines show the results when we have taken into account these collisions. And we can see that the magnetic field that we have obtained is larger when we take into account the coupling between the two fluids. And now if you go to the next slide, please. So we have studied the dependence of this generation of magnetic field on the ionization degree of the plasma. You can see that the black symbols in the plot on the top corresponds to simulations where there is no coupling between the two fluids, and in this case, there is no dependence on the ionization degree. On the contrary, when there is coupling between the two fluids, we can see that there is an enhancement of the magnetic field generated, and this enhancement is larger as the ionization. Sorry, can you? Oh, is my time over?
No, sorry. I was doing other things and I moved your the slide. Is this one? Sorry.
There is one. Yeah, that one. Okay.
So but you have to finish more or less soon.
Yes. Well, finally, we have also studied the dependence of these results on the total density. This is shown in the bottom plot, and these results show that as you increase the total density of the plasma, the magnetic field obtained is larger, and the results of the two fluid simulations converge to the single fluid model, which is here represented by the solid black line. That's all. Thank you.
Thank you very much, David. And our last presentation will be given by Andrea Perdomo Garcia.
Hello, can you hear me?
Yes.
Okay. Here I'm going to show the first preliminary results of the simulations that I've been doing during the first year of my PhD. We've done boxing star simulations for a K05 star with the Mancha code, and we also compared this with the solar case. Here we can see an horizontal cut showing convection around optical depth equal 1 for both the K05 star and the sun. In the left is the temperature, and in the right the density. In pink and yellow small plots are the K05 star, and the big ones are the solar case to compare. As we can see in these images, we find smaller convective cells and lower temperature contrast for the K05 star compared with the sun. Can we go to the next slide, please? We also have studied the formation of magnetic field in the quiet regions. In particular, we use Biermann's battery term as a seed for the magnetic field and local dynamo action to enhance it. And here we can see the evolution with time of the mean value of this magnetic field around optical depth equal 1 for both the sun and the K05 star, after introducing this Biermann term in the equations. It's apparent that the K05 star reaches a saturated value of the magnetic field sooner than the sun, and it goes from around 10 to the minus 7 Gauss to 100 Gauss. This is the interesting part of the study we've done here, because it reaches values similar to what we found in simulations for the solar case. We plan to analyze these results further, and since I've said at the beginning this is preliminary, and do this study for other spectral type stars. And that's it. Probably I was too quick.
No, it was perfect. Thank you very much for your presentation. And we are done with this set of presentations and almost in time to close the session. We still have 1 or 2 minutes, perhaps, if there is any question, or I don't know, Sarah, if you collected questions or comments.
Yeah, well, there were some questions from the audience in the chat tab, from Valentin to Consuelo and from Valentin to Christoph, and they were already replied by the authors. So if any of you have any question or suggestion, we'll be very welcome.
It doesn't seem to be the case.
No, so remember you have also the solar physics thing on Slack. So if you have any questions or anything, you can also type in there. And that's all.
Okay, so yes, this was, we were in a hurry. It was a bit difficult, but I think we did pretty well. And so again, if you have questions, you can perhaps contact the authors offline and ask them. So thank you very much for your participation and for your contributions. And I remind you that the SEA assembly will take place in 4 minutes from now. So if you are interested, just connect to that session. Again, thank you very much, and enjoy the rest of the meeting.